Hello friends, welcome back to the data structure tutorial, and today we will be discussing about non-linear data structure. In the previous videos we have discussed about the linear data structure. Those are arrays, stack queue, circular queue and a linked list. And how the non-linear data structure is different from the linear data structure. The basic example is, in the linear data structure we were accessing the data in the sequential way, that is one after another. But in the non-linear data structure we will be storing our data level wise. So this non-linear data structure is categorized in two different types. Those are graph and tree. We'll be having a separate video series on the graph, and in this video we will be talking about the tree. But let us understand what is graph. So in the simple word, the graph is a collection of nodes or vertices and edges. So what it means, nodes and vertices means your information. Let's say we have a node A, then this independent node is also called as a graph. If there is another node, suppose B, then collectively it's a collection of A and B, so we can call this as a graph. Let's say we have another node C which is containing some information, then collectively A, B, C are called as a graph. It's a single graph. So why? Because it's a collection of these three different nodes. But if you want to connect them, so you need an edges. So with the help of edges, it represent the exchange of data. So A and B are connected now. So collectively you can call this as a graph. Then if it is connected to the C, again it is also called as a graph. The previous type is called as not connected graph, and now we are drawing the connected graph. So this is also a graph, and if you draw this edge, then also it is called as a graph. Okay. Now what is tree? Tree is a subtype of graph. It's a subtype of graph. So what is the difference between them? Okay, we understood that it's a subtype of a graph. So it will also have the vertices or the nodes and edges. So let's say we have a node A again, and there are different nodes again, suppose B and C. Then this is not a tree because tree should be connected. It should be connected. So tree should be connected. And now if it is not connected, then it is not called as a tree. Okay. If we connect it, then you cannot connect B and C. Why? Because tree is a graph without a loop. If you observe the first condition, the graph A, B, C is collectively forming a loop. Means you can, starting from A, you can go to the B, you can go to the C, and you are coming back to the A. So you are completing a loop. So that is not allowed in a tree. So if you connect this, it is not a tree. But now if you are connecting all the nodes without any loop, then this is called as a tree. Then tree is a data structure used to hierarchical representation of your data. Now how to represent a data in a hierarchical way? So let us take an example. All we know that the working of any organization. So let's say we are taking an educational organization. So the highest post is principal. So principal is a topmost position, and under this principal there are several head of the departments are working. Let's say head of the department of mechanical department, then head of the department of a chemical department, and head of the department of computer science department. And under each HOD there are different faculties are working. Let's say we have the teaching faculty and non-teaching faculty. Same for other department also, teaching faculty, non-teaching faculty. Here are also teaching faculty and non-teaching faculty. Again for the teaching faculty we have the different teachers. Non-teaching faculty we have the different peons and all other non-teaching staff. So you can say it's a non-teaching faculty. Same for this and this. So what we have just done, we have represented the information about the educational organization in the hierarchical way, and that is the use of tree. Now if you want to access a particular information, you can easily categorize that. You have the you have a separate path to for that department than for the particular category like teaching faculty, and they can you go to the particular teaching faculty. So you do not need to scan the entire data of your tree, and that was the drawback in the linear data structure, that we have to scan the entire data structure, or we need to visit that node in a particular sequence. Here is a sequence, but the data is efficiently categorized. So let us talk about the terminologies used in the tree. So I'll quickly draw a tree. Let's say we have a tree with node A, node B, node C, then again it is connected to the node, suppose D, E, it is F and G. So we have a tree. The node which is representing the top of tree, this node is always called as root node of your tree. Then the nodes which are internally represented, those are called as internal nodes or non-terminal nodes. And the nodes which are at the bottom of the tree, those are called as the leaf nodes, leaf or terminal nodes, which are representing the end of your tree. Then there are few more terminologies also, like parent. So you can say that A is a parent of B and C nodes. B can be a parent of D and E. You can see B is a parent of D and E. C is a parent of F and G. So it means that the nodes other than root which having the children are called as internal or non-terminal nodes. Okay, and the nodes which are not having any children, which do not have any children, those are called as the leaf nodes, and them also we can call as the child nodes. So you can say that child nodes are B and C are the child of A, root node A. D and E are the child of B, and F and G, the nodes, are the child of node C. So remember this terminology. So whenever we are talking about the parent, you have to remember this terminology. The node which having the children are called as the parent node. Children means a node which has the parent are called as the children nodes. Then the leaf terminal nodes means these nodes which are at the end of your tree. Internal node means other than root and leaf node, called as the internal nodes. Now there is one more terminology. Let's say we need this part of your tree only. So this part is called as a subtree. So if we have the entire tree, and out of that we just separate out the three nodes B, D, E as a subtree of your entire tree. So remember this terminology. Now let us talk about the types of tree. Now what is binary tree? So binary tree means you can have at most two childrens, at most two childrens. Any node of your tree can have at most two childrens. It means that any node can have 0, 1 or two childrens. That is allowed. So let's say we take an example, the root node A. So suppose root node A do not have any childrens. Okay, it is a binary tree. If it has only one children, which is the left children, okay, it is also a binary tree. Suppose root node A having only one children to the right hand side, then it is also called as binary tree. Suppose a node having two children's left as well as right children, then also it is called as a binary tree. Suppose there is a root node which is having a node B, C children B, C and D. This is not a binary tree. Pi means 2. So maximum means at most two children can be allowed. So If there is a no children, okay, there is only one children, okay, left children, only right children are allowed. If you have both children, okay, no issue, but you cannot have more than two children, so this is not allowed. So that is a binary tree. So if you expand the tree, let's say A having the children's B, C and C also having a children, suppose D, E and E also having a children, F and G. Okay, this is a binary tree because every node having a maximum two childrens. At any level you can have a children, but it doesn't matter, but maximum there should be the two childrens. Now let us discuss about the second type, that is full or strict binary tree. So what it means that it will allow either 0 or two childrens. It will allow 0 or two childrens. So let's take an example. Suppose we have a node A, okay, it can have the no childrens, then it is called as a binary tree or a full or strict binary tree. Suppose it has only one children, then it's a binary tree, because in the binary tree you will be allowing one children, but it is not a full binary tree or the strict binary tree. So if has the another children, so A has a two children, okay, now it is a strictly binary tree. Now again if C has the two childrens, okay, then again it is called as a strictly binary tree. But if suppose I draw a children to the B as only left, okay, this is not a strictly, it's a binary tree but it is not a strict binary tree. Why? Because B is having only one children, which is not allowed in the case of strictly binary tree. So this case it is not a strictly binary tree or the full binary tree. Now let us discuss about another type, that is almost complete binary tree. So almost complete binary tree means you have to follow a certain levels of children. Let's say we have a node A, then suppose you want to have the children for this node like B and C. So there are two ways to have the children's, suppose B, and the another possibility you can have the B as a right children of A also. Okay, but there is a sequence which you need to maintain, that your level should be filled from left to right. So if there is a tree A having a right children B, then this is not a almost complete binary tree. It should have the left children filled first, then only it can have the right children. So in this case the left children is null. It means that you cannot directly have the right children. So that's why it is called as almost binary tree. Now let us take another example. Let's say we have a node A, then we have a children left children B, okay, no issue. Then we can have the right children. Again you can have the left children and right children, okay. Now here whether it is a almost complete binary tree, this is not a almost complete binary tree. Why? Because we have a root node A, the left children is filled, okay, then you have the right children, okay. Now by the level wise, what we were expecting, B should have the left children first and the right children, then you can have the children for C and C, that is D and E. So from the level wise those children are missing, so this is not a almost complete binary tree. Now let us take another example. Suppose A, B, C, then suppose B have the left children, okay, then B also have the right children, suppose E, okay, it's a almost complete binary tree because level wise it is okay. As it is a binary tree, any node have the maximum two children, so A have the maximum B and C from left to right, then B can have the D and E, okay, so it's a complete binary tree. But if I add the node, suppose F here at the right hand side of C, then again it is a false condition for your almost complete binary tree. You should fill the left children first and then only you can have the right children. So I hope you understood the concept of almost complete binary tree. Okay, now we will take one more example. That case was remaining. Suppose we have a node A, then we have the left children B, okay, then we have a right children C, then we have the next level of children, suppose D, left children, right children as E. And then again we have the left children of D as F. Now whether it is a almost complete binary tree, yes or no? No. Now why it is not almost complete binary tree? What I told you that it should be filled level wise and it's a binary tree. So A can have the maximum two children. Okay, so first it has the B left one, then it have the right one. Now on the next level B is having left children and right children E. But what is the next we were expecting? We were expecting C, the level should be filled. So C should be filled with these two children's. Then only it can go to the next level. So which is not followed, the level is not completely filled. That's why it is not a almost complete binary tree. Okay, so level wise it should fill all the required nodes from left to right. Suppose C were having the node F and this was not there and the right children is missing. Okay, then we can call it as a almost complete binary tree. Now let us discuss about another type, that is complete binary tree. So now complete binary tree means it should not be with a missing children. Missing children not allowed. Not allowed. So what it means? So let's say we have a tree node A, then it's a binary tree, so it has a maximum two children. Okay, we will be having it. Then suppose D, E and F. Now by the definition it is a almost binary tree, but it's not a complete binary tree because the right children is missing. So if you add the right node here, then it's a complete binary tree. Okay, now let us take another example. Suppose we have a node A, B, C, D, E. So whether it's a almost complete binary tree, yes it is, because level wise it is okay, but it is not a complete binary tree. Why? Because C having the missing childrens. So what it means, if you add the nodes, suppose F and G, then the leaf node should be at same level. If any parent is missing his children and all the leaf nodes are not at the same level, so in the previous case, suppose B and C are the children of A and then B having the two children, that is D and E, and C was the only last child. So the children nodes are D, E, C. So all these three are the leaf nodes which are not at the same level. So that's why it is not a complete binary tree. So every tree should have all the leaf node filled at the same level, then only it is called as a complete binary tree. It means that every node internal should have the two children and all leaf nodes should be at the same level, then only we can call that tree as a complete tree. Now in the next video we will be discussing about how to traverse this tree, means how to visit this node. There are different techniques to visit each and every node of your tree for the further operations. So we'll see you in the next video.